We're here with Dr. Bruno Tomberli of Capilano University to discuss the transit method of planet detection, of exoplanet detection.
So transit method is one of the most prevalent methods of planet detection. It relies on the fact that when a star has planets revolving around it, sometimes the planets get in between us and the star and block some of the light. So if this is a star, you can imagine if it has planets orbiting around them, if they're orbiting, say, this way, we'll never see them, but with this method at least. But when it's orbiting this way, there will be times where the planet crosses in the line of sight and blocks the light that would have come from this part of the star, so that you would actually see a reduction in the intensity of the starlight. So how this looks when you're collecting data is if you have an intensity versus time plot. If you're just looking at the star normally, you'll just see it. That you'll just have data all over the place like this.
Now, we're now talking about when you use a CCD or something to detect it, not just visually.
Yeah, I'll comment more about that in a second. But this wouldn't be visible to the naked eye, although in principle, if humans had enough sensitivity to intensity, you could actually see this with the naked eye. Certainly, when the moon does this to the sun, we pick up on it. But if you've ever seen an eclipse, you'll notice until you're over 90% eclipsed, you almost don't notice there's anything going on. It just seems like, oh, a slightly cloudy day or something. But at this point, the planet's over here. It's not blocking any of the light. And then when the planet crosses in front, like I say, this light doesn't come anymore. And what you notice is a reduction in the intensity of the starlight, about 1%. Now it's falling down here. And then as the star passes, as the planet goes past the star, the light returns to its original intensity. Okay, now these little variations, this bouncing around that I'm showing here, is caused by atmospheric turbulence, if you're looking at this from a ground-based telescope, instrument variations, the telescope's wobbling a bit, the star itself has some variations, so you never get this perfect flat line sort of situation, but you get these variations, but because the variations are rather large, about 1% is typical, they're quite observable using a charged couple device, which is what your mobile phone camera uses. So these are quite ubiquitous, common devices. What you do is you point your telescope at a star that you're trying to see if it has a planet or not, and you wait. But once you've pointed the telescope at the star, you track it, so you have something called an equatorial mount that keeps your telescope pointed at the star for a period of a few hours. This range here is typically a few hours. And you defocus it because you don't want the light to saturate any part of your telescope. A focused image produces very sharp, bright spots. Like a star will show up as a very bright spot, which means you won't capture all of the light. Some of the light you'll throw away because it would like burn a hole or damage the CCD in some way. So you put a diffuse patch of light, and that way you don't throw away any of the photons. You can count them all, and you get a 1% variation like this shows up very clearly. So what's amazing about the process is that that if this is a yellow star, say like our sun, by the color of the light that you're detecting, you can tell very accurately what the size of the star is. So what that tells you is this amount of time, say this is 40 minutes or an hour, it tells you how long it took to travel. And because the rays of light are perfectly parallel at these large distances, you know how fast this planet traversed the face. If it was very fast, you know this planet, the orbit was very close. If it was very far, it will take longer. And this part of the graph will be stretched out. So you'll quite clearly know the length of this orbit, whether it's a close orbit or a far orbit. So once you know the size of that orbit, that's a great thing to know, so you can tell whether it's in the habitable zone for that star, how much starlight it's receiving, how warm that planet will be, whether liquid water is a possibility on that planetary surface. Also, the amount the light dips by tells you the size of the planet. So if it's a bigger dip, then you know it was a bigger planet, not just this little red dot, but something bigger has crossed in front. In conjunction with other methods for planet detection, such as the Doppler method, you can tell the mass of the planet. So if you know the mass of the planet and the size of the planet, you can infer the density of the planet, which will tell you whether it's made out of water or ice or rock. So you can tell an awful lot about a planet from just a few simple measurements that could be done by hobbyist astronomers.
Oh, thank you.